Hello students, this video lecture will cover section 11.1, space figures and cross sections. Our learning goal for this lesson is to be able to recognize polyhedra and their parts, and to visualize cross sections of space figures. So let's go ahead and get started. First, we need some vocabulary. A polyhedron is a space figure or three-dimensional figure whose surfaces are all polygons. Each polygon is called a face of the polyhedron. The edges of the polyhedron are segments that are formed by the intersection of two faces. Much like a two-dimensional object, a vertex of a polyhedron is a point where three or more faces intersect. So our first question is an identification question. It asks us how many vertices, edges, and faces are in the polyhedron below, and asks us to list them. So let's start with the vertices. When I list the vertices of a polyhedron, I just write down all of the points that make the polyhedron. And as I write them down, I cross them off the figure. So I have R, I have U and V, I have S, T, and W. So this polyhedron has 6 vertices. As far as edges are concerned, I'm going to do the same thing that I did with the vertices. I'm going to outline the edge and then I'm going to write it down. So we have U to V, we have R to V, we have R to U, we have V to W, we have U to T, we have R to S, we have S to T, we have T to W, and we have S to W. So one last check over the figure, make sure all the edges have been identified. And if you count those up, we have 9 edges. The faces of a polyhedron are all going to be planes. So if we remember back to chapter 1, we need at least 3 points to represent a plane. So the first plane that I'm going to recognize is plane STW. That's this back edge of the triangular box. So then the next plane that I'm going to recognize is RST. That's this rectangular side of the triangular box. I'm going to recognize RSW. That's this slanted ramp face of the triangular box. I'm going to recognize UTW. That's the bottom rectangular face of the box. And finally we have RUV, which is this front triangular face, the face that appears to be the closest to us. And so if we count up the faces, we find that there are 5 faces. So one of the key concepts for this lesson is Euler's formula. It states that the sum of the number of faces and vertices of a polyhedron is 2 more than the number of its edges. So we get the formula F plus V equals E plus 2. So we can use this formula, Euler's formula, which again states that F plus V equals E plus 2, to find the missing number of a given polyhedra. So let's write down the formula. We have F plus V equals E plus 2. Here the number of faces is a variable. So we have F plus V, which is vertices. So we have F plus 20 equals the number of edges, which is 30 plus 2. So we get F plus 20 equals 30 plus 2 is 32. And if we subtract 20 from both sides, we get that F equals 12. So this is in fact a 12-sided polyhedra. Same thing for the second problem. We have F plus V equals E plus 2. In this case, we have 20 faces plus 12 vertices equals the number of edges plus 2. So over here we get 32 equals the number of edges plus 2. And if we subtract 2 from both sides, we get that there are 30 edges to this polyhedra. One thing that's really important to remember is that Euler's formula is slightly different in 2 dimensions. So first, let's verify Euler's formula for the solid. So if you remember, the formula is F plus V equals E plus 2. So let's count up the number of faces here. This object has one back face, which is a trapezoid, one front face, which is a trapezoid, and then 4 rectangular faces, which represent the sides of the trapezoidal prism. So this object has a total of 6 faces. If we count up the number of vertices, we have 1, 2, 3, 4, 5, 6, 7, 8 vertices. So on the left-hand side of the equation, we have 6 plus 8. We simplify 6 plus 8. 6 plus 8 is 14. Counting up the number of edges, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 edges. So there are 12 edges, and if we take the 12 plus 2, 12 plus 2 is 14, so the formula does hold true. So now we go all the way back to chapter 1 to draw a net for this solid. The solid is going to have 2 trapezoidal faces. So one on top, one on bottom. They're going to be connected with a rectangle. And they're going to have 4 rectangular faces. So we have one side, this would be the top, and then we can put the other side over here. So Euler's formula for a 2-dimensional solid should say something like F plus V equals E plus some number. Now there are still going to be 1, 2, 3, 4, 5, 6 faces. So we count up 6 faces. If we count the number of vertices, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 vertices. So we have more vertices in a 2-dimensional net than we do in a 3-dimensional object. And that should make sense because when we fold these vertices up, they're going to meet each other. So if we combine like terms over here, we get 20. Let's count up the number of edges that we have. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So we get 19 edges. So the question mark over here, we end up with 20 equals 19 plus something. Well, that something is going to have to be a 1. So Euler's formula for a 2-dimensional net is going to say that the number of faces plus the number of vertices equals the number of edges plus 1. So let's talk about cross sections. A cross section is the intersection of a solid and a plane. We think of cross sections as an extremely thin slice of a solid object. So here you can see we have a triangular prism that's being cut by the yellow plane. And where the yellow plane cuts the object, we can see the cross-section is a triangle. So if we want to think about what cross-sections would look like, oftentimes you'll find that I draw dotted lines. So I'll connect the different points with dotted lines, and I'll see what kind of object that looks like it might be. Most likely, if we wanted to draw this cross-section, the cross-section would look like a rectangle. So let's talk about the cross-sections formed by cutting a solid object with a plane. If we were to draw a horizontal plane that cut this object, we have to think about what this would look like. So it looks like the top of this object, the horizontal top, is a circle. It looks like most likely the bottom would also be a circle. So as long as we cut horizontally along any plane, it would look like we would get a circle. Now, if instead we were to cut this with a vertical plane, It looks like by cutting it with a vertical plane, we would most likely get a trapezoid. So question 5 asks us to draw a cross-section formed by a vertical plane that intersects the front and right faces of this cube, and wants to know what shape the cross-section is. So again, I want a vertical plane, so I'm going to draw vertical lines on both the front and right-hand faces, and I'm going to connect them at the top and bottom. So this is a portion of a vertical plane that cuts the front and right faces of this cube. And again, we have to be cautious because we're looking at this three-dimensionally, even though the cross-section is a two-dimensional object. So if we were to draw this in 2 dimensions, we would find that again, this cross-section is going to be a rectangle. That concludes this video lecture on section 11.1, space figures and cross-sections. Hopefully now you understand how to recognize polyhedra and their parts, and you're able to visualize cross-sections of space figures. Thank you for your attention, and I'll see you soon.